several times, so I'm not going to cover it again here. I'll let you read through this slide and look at this diagram for clarity. So pathogen binding to the toll-like receptor through the PAMF, that causes the release of cytokines, specifically things like TNF-alpha, or tumor necrosis factor, I'm sorry, shouldn't call it alpha anymore, which cause inflammation, and they also recruit white blood cells. So when you have pathogen and neutrophil binding, and you do get that cytokine release, what you're going to have is vasodilation of the blood vessels. That allows them to become permeable, so things can come out, like white blood cells, into the region, and that causes inflammation, by the way, which then controls the pathogen from being able to move, so that these white blood cells can then find that pathogen. Once they're done, they can return to the lymph, or the pathogen can even go into the lymph, but if it goes into the lymph, you're going into a node or a nodule where there are other white blood cells waiting for phagocytosis. So this just shows you a lymphatic capillary, and the interstitial fluid, which came out of the blood vessel, can go back into the lymph. So phagocytosis is the ingestion of microbes or particles. Neutrophils are early in infection because there's just a lot of them. Macrophages, however, soon pick up because they start to wander into the area where the cytokines are leading them, saying that there's a pathogen over here. Fixed macrophages, however, they stay in a node or a nodule. It's only the wandering ones that will go to the area of infection with the neutrophils and do phagocytosis. So remember, PAMF, toll-like receptor binding together, that allows us to do phagocytosis to make a phagosome. That phagosome will then fuse with the lysosome to make what's called a phagolysosome, and then that pathogen will be digested in the phagolysosome. Then you release the waste for that that debris that was digested by the lysosome. And if we were actually to talk about acquired immunity, adaptive immunity, we would say that you would also present some of that on a MHC class 2 receptor. However, we're talking about innate immunity here, so we're not going to talk about that right now. So that's what this slide says. And then TNF is a cytokine chemical signal alarm for other white blood cells to go there and cause vasodilation, and it also recruits complement proteins. And it stands for tumor necrosis factor, TNF. So when a neutrophil arrives on site, it can do phagocytosis, but can also do something like an oxidative burst. An oxidative burst creates hydrogen peroxide. That hydrogen peroxide forms free radicals, which are called the ROS, the reactive oxidative species. They bind to DNA, mutating the DNA. If you create a lot of hydrogen peroxide, which is what happens during an oxidative burst, it will bind to a lot of DNA, causing a lot of mutations, with the goal that those mutations will then cause the death of that pathogen. However, if a pathogen has the enzyme catalase, so they're catalase positive, they take hydrogen peroxide and render it useless by creating water and oxygen. So an oxidative burst on a catalase positive strain, something like Staphylococcus aureus, is useless. Okay, so how do microbes evade this phagocytosis that happens? Well, they can have things like capsules, and we talked about capsules being another layer, which makes it more difficult to get around and be able to bind to through your toll-like receptors. They can kill the phagocyte, so that's what a leukocytin does, is it's going to release lysosome enzymes in the cytoplasm, and that causes things to lyse, and that kills the macrophage or neutrophil or dendrite. You can lyse the phagolysosome, so when they fuse together, you can have that lyse. You can escape from the phagolysosome. You can prevent fusion of the phagosome and the lysosome. And then some of them, well, they just plain survive in the phagolysosome and never get digested. And remember, bacteria in a biofilm community are more difficult to phagocytose than free-floating bacteria. So you engulf a pathogen, the debris are broken down in the phagolysosome and then released. Well, how does that happen? So the plasma membrane, toll-like receptor PAMF bind, this surrounds it, brings it in, that's the phagosome. You then fuse that to the lysosome to create the phagolysosome, which then cuts up the pathogen and then releases some of the pathogen, or you can even present it as well. And here I show that if you're going to bring in that pathogen, the plasma membrane is going to pinch off and create that phagosome. So the second line of defense that we're going to talk about for innate immunity is inflammation. And inflammation is important because it's going to prevent the pathogen from being able to move around, and it's going to cause vasodilation, which allows more white blood cells to enter into that arena. So activation acute phase proteins, complement proteins, cytokines, and kinins, vasodilation caused by histamines, kinins, and prostaglandins. So there is redness, swelling, because the blood vessels have vasodilated, which allows fluid to come out, which is called edema. There's going to be pain, there's going to be heat associated with it, and it can be acute or chronic. Chronic inflammation overall is more damaging to the body, obviously, because that pressure is also being exerted on your cells, which over time can be detrimental and stressful to those cells and can actually lead to apoptosis. What I should say is the complement here are proteins floating around. These are activated by the presence of the pathogen. So inflammation destroys injurious agent by removing its byproduct. We can, if destruction is not possible, limit the effect by walling off the injurious agent. So then we will do fibrinogen to create a clot, so that you can't move past the clot. Repair or replace tissue damaged by the injurious agent. All cells involved in inflammation have receptors for the cytokine TNF and produce more TNF upon activation, so that you have a cascade of TNF being produced, which causes more inflammation. So pathogen, probably a neutrophil. The toll-like receptor binds the PAMP. We then bring it in, phagocytose it in, and then the cytokine is going to be released. That causes vasodilation, which allows the white blood cells to leave the blood vessel, and we also get swelling, which prevents the pathogen from moving around. The pathogen can still enter into the lymph, but it'll go to a node or nodule where there's more white blood cells like the fixed macrophages waiting to phagocytose it. So kinins cause vasodilation. Neutrophils are also attracted to kinins through chemotaxis. So like it's an alarm that says go over here, and they can sense that kinin presence. Prostaglandins released by damaged cells intensify the effects of histamines and kinins. So vasodilation can be caused by histamine. So neutrophils can release chemicals that cause the basophils to release histamine. And so when neutrophils are the first to attack, they release cytokines that causes the histamine release from the basophils. Leukotrienes increase blood capillary permeability and help attach phagocytes to pathogen. And again, vasodilation helps bring in clotting factors because it makes the blood vessels permeable. This just shows you that if you have a wound, you're going to have what we just talked about, and then you're going to form a clot, which is called a scab as well, for protection of the tissue. This tells you what the histamine, the kinins, and the prostaglandins do, and the leukotrienes. These are all chemical signals that are released by the basophils, or a mast cell. So phagocytes move neutrophils that